Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, I will start working with you to find areas moment of inertia, because moment of inertia would be very important for you, whether you are doing like classes in physics or engineering. So the moment of inertia is like it's how the body resists rotation. Like it's it's the it's basically that's what you will learn later. Sorry. It's uh, it's a property of the area or the mass for that matter, because you can find the mass moment of inertia. It's the same concept. And just to give you an idea, this is like it's the how the body let's take an example to illustrate that. Um, how do I show you? Okay, let's draw a rectangle. That's probably the easiest thing to show. So if I draw a rectangle of, say, base B and height h, and those of you who are doing some structural analysis like mechanical engineers or civil engineers, you know exactly what we are talking about here, the moment of inertia and how it's important. And let's say here is the axis of the centroid. So I'm going to use a dashed line here in the middle uh, to show that. Hmm. Now, as you know, in structural analysis first, and then later you can think about the rotation moment of inertia. But for the time being, let's say I'm going to call the bottom here axis x. So this is the x and the y. And this is the x sub c, or the centroid, which is at a height of h over 2. So you can say this is h over 2, and this is h over 2. So if 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 this part of a beam and this beam is loaded, so you have some weights here acting on it, you can see that this anytime you apply forces on a body, this body get deformed. And this deformation causes, which we call a strain, and this strain causes stress in the material. So this material has to be designed in a way that it can withstand that stress, meaning it has its own strength higher than the stress applied, so it doesn't break, like doesn't shatter for the time being. Maybe we'll discuss that in more detail later. So you can see that if I place the beam like that and I apply load to it, it will deform. Of course, you cannot see it with your eye unless it's made of, say, timber or something that is really will uh, deflect, but it's going to deflect. I'm exaggerating here to show you what will happen to the body. So the bottom fibers would be under tension. It's like you are pulling them, but the top one are under compression. And there is a neutral axis in the middle where there is no tension or compression. You know, tension and compression are opposite to each other. So if the tension we consider it as positive and the compression as negative, you cannot go from positive to negative without passing through the zero. So again, this is a topic for another day, but the neutral axis is an axis that is neither stretched nor compressed. But what if I take this beam and turn it over like that? So mean that the base and that the height, and apply the same loads. Do you expect that that beam that has this base and that height will be like deflected the same or more or less than that beam? Think about it. It's pretty common sense. If you said it's less than that, then of course you are saying you are, see, here is a beam. That's this uh, I'm going to have this piece. Is it? Can you see it? I don't know. Yeah. So I'm going to say if I place it like that and try to push it down, or I make it like that and try to push it down. Do you see that um, the the deflection, of course, you cannot see any deflection, but the hypothetical deflection would be less in this case when the height is very big versus that when the base is much bigger than the height. And we'll see why. So what resists that deflection is the section moment of inertia. So we need to find, first of all, define what is the moment of inertia, and then uh, see how we can find it. So let's take again the same easy example of a rectangle. But before saying that, we say that the moment of inertia about the axis x equals the integral of y square dA. It's the second moment of the area. Okay, so if I'm finding it about Ix, it's the second moment of inertia, second moment of the area around this line. If I make it about the centroid, it's the second moment of the area about the centroid. And you will see that taking the second moment about the centroid for any shape is the minimum moment of inertia you can get. Those of you who were following my sessions of probability and statistics, you would find a very similar thing when we were calculating the the variance. The variance, okay? The variance of a distribution is the second moment about the mean, which is basically the centroid. To find the centroid, remember again, if you follow the sessions of engineering statics, you see that you were taking the first moment about the origin. And the first moment about the origin gave me the mean. The second moment about the mean gave me the variance. But we also could find the second moment about any line, about the x-axis or the top or anything, okay? In the case of a rectangle, because it's the same cross-section from bottom to top, it's really easy to find the moment about the x-axis or about the centroid. We'll see how we do that. First of all, you already learned what is dA, which is the area of a small element of height dy, right? So if I take a small piece here, a small element of height dy that is y away, the perpendicular distance is y from the x-axis, I say that dA is the area of that element. And what is that, the area of that element? dA is basically B times dy, right? It's a very small rectangle. So that's the simplest case you would have. So if I want to take the moment about x, which is that, I would say, okay, I'm integrating y from 0 to h, right? The total height. Y square, b is a constant, so I can take it out, dy. You see how easy it is? They are simply integrating y squared dy, which is y cubed. So you get b y cubed over 3 evaluated from 0 to h. So it's b h cubed over 3 minus 0 equals b h cubed over 3. Very simple, right? But we said this is not the smallest moment of inertia. The smallest moment of inertia occurs about the centroid, which is I x c. So if we don't know any better, I'm going to say it's the same thing. It's b times the integral from negative h over 2, because I'm taking the moment here. So this point has a height of negative h over 2 to positive h over 2 of y squared dy. Some of you can take the moment from 0 to h over 2 and multiply it by 2, but let's do it. Let's play it here as you would do, I'm sorry, y cubed over 3 as before, but now I'm going to evaluate it from negative h over 2 to h over 2. So I will get b, as I told you, we open two brackets with two pairs of parentheses in between and a negative sign between them. And you would say h over 2 cubed, I'm sorry, h over 2, yes, h over 2 cubed, and I can take the 3 out as minus, and this is negative h over 2. When you cube it, it becomes negative h cubed over 8, since, well, negative h over 2 cubed, since. So this would be b over 3 times h cubed over 8 minus negative times negative is positive, so plus h cubed over 8, which add up to h cubed over 4, so you get b h cubed over 3 times 4 is 12. And that's the smallest moment of inertia that this shape has, or this area has. Now, maybe we can introduce, without proving, uh, a very important law that says it's called the parallel law, or the parallel line law of a moment of inertia. If I know the moment of inertia about any line parallel to the centroid, parallel to the axis of the centroid, I can find the moment of inertia about the centroid by taking this moment of inertia. So if I want I x sub c, I can take I sub x, where x is any axis parallel to the line of a centroid, and then I subtract the area times the perpendicular distance, which in this case is x sub c squared. By the way, this is the same we do in probability and statistics. You can take the second moment about the origin and you subtract the square of the mean. Notice the area is 1 under probability distribution. So when you subtract x sub c, which is the mean square, you get the variance. Same. Okay, so here I can say it's bh cubed, I'm sorry, I said h cubed over 3 minus the area, which is bh, times h over 2, which is the distance from the centroid quantity square. So I get bh cubed over 3 minus bh cubed over 4. I take a common denominator of 12. You divide by 3, you get 4. Minus, when you divide by 4, you get 3. 4 minus 3 is 1, so you get bh cubed over 12. And if you know the moment of inertia about the centroid and you want it about another axis parallel to it, you would add a times x sub c squared. If you know it, here you have to be very careful. If I know the moment of inertia about the base, okay, about the x-axis, and I want it about another axis, not the centroid here, what would you do? Suppose this height, let's call it y1. How do I find uh, the moment of inertia about this axis? If you say do it the same way as you did, no, that is not correct. You always have to go back to the centroid moment of inertia and then add. Meaning, in order to find the moment of inertia about this line, I'm going to say it's bh cubed over 3 if I didn't know the moment of inertia about the centroid. Subtract the area times h sub 2 squared to get the moment of inertia about the centroid, and then add the area times this height, which is h over 2 minus y1 squared. So going to the centroid, you subtract, going away from the centroid, you add. But you cannot go between two parallel lines that neither of them is the centroid. If you know it about the top and you want it about the bottom, you have to subtract the area times the square of the centroid to get to go to the centroid, and then add the area times that distance squared. Okay, very important because I've seen students going and say, oh, it's the parallel law, so just subtract the distance and go from x to this. No, it's not correct. Okay, so this law is very important, and I introduced it here because the next one I'm going to do is the moment of inertia, say, of a triangle. Okay, so let's say I have my x and y. And let's say I have some screen triangle. So let's say it goes something like this. And again, this is the height, h, and that's the base b. You should know from the work we did for the centroids in the engineering statics course that the centroid lies at the height of h over 3. Okay? And we want to find the moment of inertia here. It might not be easy. It is, I mean, it's doable, but it's not easy to find the moment of the moment of inertia about the centroid. The math is a little nasty. It's easier to find it about the base and then subtract the area of the triangle, which is 1/2 b times h, times the distance h over 3 squared. So let's do that and see how we can do it. So I sub x equals. Now, I know it's the integral of y squared dA. But how do I find a strip and find the area of that strip or that element? Okay? So if I take again a small piece here of height dy at a height of y, and call that base x and the height dy, I can say that dA equals x dy. That's a problem because I'm integrating with respect to y. What is the relationship of x to y? Okay, like we did before, and we said this height is y, then the rest of the height would be h minus y, right? H minus y. And I can see that this small triangle and that large triangle are similar. So I can find the proportion of this height over the total height equal this base over the total base. And that's how I can transform the x into y. In fact, I could have done it by looking only at the right-hand side and say that's the equation of a straight line, and that's the equation of a straight line, and then take it. It's very hard. Not hard. It would be easier if it's a right triangle. You can do it in many, many ways. But here it's much easier to say that the base x of the small triangle divided by the base B of the large triangle is the same as the height of the small triangle over the total height, or the height of the big triangle. And from here, I can find x to be b over h, which is a constant, remember, times h minus y. So now I can take the integral from 0 to h as before of y squared times b over h, that I can take it outside of the integration since it's a constant, h minus y dy. So this equals b over h times, I'm going to integrate hy squared, or if you want, just we can distribute, you can see it. It's hy squared minus y cubed dy. And now when I integrate that, I get hy cubed over 3 minus y to the fourth over 4, going from 0 to h. So it's b over h times h to the 4 over 3 minus h to the 4 over 4. Again, we did that for the rectangle when we took a common base of 12 and we got h. Notice that I can simplify the h with those, make them cubed, and I will get bh cubed over 12, which is the moment of inertia of a rectangle about its centroid. But for the triangle, it's about its base. So finding it about the centroid is easy, right? The centroid here, as we said, is at the height, at the height of h over 3. By the way, those of you who are old enough to use like watches that are not digital, like analog watches, you notice that we divide it into 60 minutes, right? The hour is divided into 60 minutes, and 60 is a nice number. You say, why? Well, 60 or even the 12 is a nice number because the 12 is divisible by 2, by 3, by 4, by 6, by 12. It's so easy. And everybody knows that h over 3, 1/3 of an hour is 20 minutes. You know that the minutes hand would go to 4, right? And when you subtract h over 4, 1/4 of an hour, it goes to 3. So 4 minus 3 is 1, and they are 12 numbers, so 1 over 12. And usually it's very easy to work numbers that, or add or subtract fractions that have a denominator of 2, 3, 4, or 6, because you can use the watch. For example, if I say add them instead of subtracting them, you say, okay, 3 and 4, right? 1/3 is 20 minutes, meaning the handle is at 4. 1/4 is the handle is at 3. So 3 plus 4 is 7. You get 7 over 12, which you already probably know. 1/2 plus, or 1/6 even, 1/6 of an hour. Notice they are 12. So 1/6 meaning you go from 0 to 2 plus 1/3, which is 0 to 4. 2 and 4 is 6. And 6 over 12 is 1/2. So a third plus is 1/6 is 1/2. And when we were kids, it was easy to add these in your head if you know the watch. And if these numbers are 2, 3, 4, 6, or 12, it's very easy. Anyway, that's now I want to find the moment of inertia about the centroid. So I say it's the moment of inertia about the base minus, notice, going to the centroid, you subtract the area, which is 1/2 BH, times the square of the distance between that axis and the centroid, h over 3 square, equals bh cubed over 12 minus bh cubed, 3 squared is 9 times 2 is 18. 1 over 12 minus 1 over 18. So notice I'm going to take a common denominator. The LCM is 36. 36 divided by 12 is 3, minus 36 divided by 18 is 2. So you get BH cubed over 36. That's the moment of inertia of a triangle about its centroid. These are common shapes. Oh, maybe you can do a circle. The circle can be done easily if we use polar coordinates instead of Cartesian. Why use Cartesian with an equation x squared plus y squared equals r squared, right? In fact, we can do it also for uh, half a circle. It's Do you remember the centroid of a semicircle? Huh. Anybody remembers from what we did in engineering statics? It's 4r over 3 pi. Anyway, if you can't remember it, it's okay. So here, again, here is my x-axis. And here is my y-axis. And then I want to find the centroid. Notice in the triangle and the rectangle, we found the moment of inertia about the base, and then we subtracted because it was hard to find the moment of inertia about the centroid directly. It's not infeasible, but it's more work. It's much easier to find it about something you know, and then just subtract the area times the square of the distance. However, for a circle, it's much easier to find it about the axis than to have it say about the base, which is like a tangent to the base at this point, right? The horizontal line parallel is like y. It's much easier to do it like that, especially if you use um, if you use polar coordinates. Remember that we said, first of all, let's write the equation Ix equals the integral of y squared dA. If you remember when we did the double integration, we found dA using polar coordinates to be r dr d theta. If you can't remember that, remember we took a very small element here. So you can take a very small sector of the circle, or any graph for that matter, not necessarily a circle, and we said this is d theta, and then we took an element here that is r away, lowercase r, from the pole, and this distance would be dr. So we said this would make a rectangle as d theta and dr. Remember, there are the limits of delta theta and delta r when theta and r go to 0, right? The limit. So that becomes a rectangle of base equal to the arc length, which is r d theta. This distance is r d theta. And the height of this rectangle is dr. So you get r d theta dr. So all what you have to do now is to take a double integration. You say, oh my God, you said it's easier and you're doing double integration? Yeah, wait a second. It's much, much easier doing that. Here, so we don't confuse the r as the variable with the r as the limit of integration, some people can use uppercase R, or call this, instead of r, they call it a, or they call the the whole radius. Let's call that A. So this is equation is x squared plus y squared equals a squared. Okay, so we don't use r as a variable and r as a limit of integration. It doesn't work, right? So we have double integration. The r goes from 0 to r or 0 to a, and the angle goes from 0 to 2 pi. So let's use two different colors. Y squared, what is y? Who remembers what is y in polar coordinates? Hmm. It's r. So any height here, y equals r sine of this angle, right? So r sine theta. So that becomes r square sine square of theta. So let's write the sine square of theta, with red. I should have done it first. Times r dr d theta. The nice thing about this integral is that the r and the theta are independent of each other. R is not a function of theta. R is simply the distance from the pole. It goes from 0 to a. And theta is a rotation from 0 to 2 pi at any given r. So they don't interact with each other. So I can break this. You learned that before, right? I can break that as an integral 0 to a. R squared times r is r cubed dr times the integral from 0 to 2 pi of sine square theta d theta. Do you see why it's much easier now? I don't have to have two variables and take the integral, in the inner integration and then transform that into the outer integration like we do in, Cartesian. No, we don't have that. The left-hand side is, or the left part of the integral is r to the 4 over 4. It's just that. And I'm not going to worry about r after evaluated from 0 to a, and that's times the integral of 0 to 2 pi. Remember how we break sine square? No, not 1 minus cosine square. That doesn't help because it's still square. Remember? Remember the double angle formula. This equals 1 minus cosine 2 theta over 2. You say, I can't remember that. Very easy. Remember, we said the double cosine angle comes in three flavors. Either cosine square theta minus sine square theta, that won't help me here at all because it transformed this. Instead of having sine square, I will get cosine square. Or twice cosine square theta minus 1, right? Because if you break that into 1 minus cosine square, so the 1 becomes -1, and the negative times negative cosine square becomes positive cosine square that add up. Or you can break that into 1 minus cosine square, so you will get 1 minus sine square. So you get 1 minus sine square minus another sine square, so 1 minus twice sine square theta. If I'm going to move this to the other side and cosine to that side, you will get 2 sine square equals 1 minus cosine. So sine square is 1 minus cosine 2 theta over 2. So that becomes 1 minus cos 2 theta over 2 d theta equals a to the 4 over 4 times the integral of 1/2 is theta over d theta. 1/2 is a constant, so 1/2 theta minus the integral of cosine is sine. Sine of 2 theta I'm sorry, cosine of 2 theta would become sine of 2 theta divided by 2. But there is another 2 here, so it would be over 4 evaluated from 0 to 2 pi. The nice thing is that sine 4 pi, when you substitute theta equals 2 pi, or even pi for that matter, it doesn't matter, you will get sine 4 pi. Sine 4 pi is the same as sine 0, right? Which is 0. And sine 0 is 0. So this thing goes away. And you get only equals a to the fourth over 4 times 2 pi over 2, which is pi. So you get equals pi a to the 4 over 4. That's the moment of inertia about the x. But because of symmetry, the moment of inertia about y is the same. And then the polar moment of inertia, as you will learn later, that's for rotation, not deflection, okay? You will have to find the moment of inertia about the pole. It's the sum of this and that. So you multiply this by 2 because you are adding ix to iy, and you get pi a to the fourth over 2. Okay, so that would be for another session if we talk about the moment, or the polar moment of inertia. Okay, so to complete our work, we can call that a x sub c, right? It's the same because x or x sub c is the same because the centroid passes through the x-axis. But let's say I want to find the moment of inertia about this line. That I'm going to call LL, line L. So using the parallel line formula, I can say ILL equals IX, or IXC for that matter, plus the area times the distance square, d squared. D here is A, that's the radius, and the area is pi r squared. So I can say it's pi a to the fourth over 4 plus the area is pi a square. I was going to write r square. And the distance, the perpendicular distance here is also a. So times a square. So you get pi a to the fourth over 4 plus pi a to the fourth, meaning 4 over 4. So you add them up, you get 5 pi a to the 4 over 4. And that would be the moment of inertia about any line that basically is tangential to the circle. I think that's enough for today. I hope you got this session. It's easy. Again, as I said, if you have any comments about the moment of inertia or how to calculate it, please don't hesitate to drop me a line or to leave a comment in the comment section. Thank you very much for watching. Hope to see you soon. Bye.